This is our snow lecture. Aren't you enjoying the weather? On induction. Okay, so the first thing you should probably do is take some notes on this lecture. I've got a document on your class page here that's titled Statements to Prove Inductively Using the Following Template. And as you go down through this, you'll see that it's got a number of statements that we're going to be looking at in this little lecture. Okay, so you might want to go ahead and print that out, or at least pull it up and have it available as we go through this video lecture. Okay, so we've done a number of examples where we actually proved statements using arithmetic series, and in every case, so we want to follow this template. Start by showing the specific statement is true for n is equal to 1. And in some cases, it may not be 1, it might be some other integer. But that's the first thing you need to do. And what I want to do is I want to go through various types of statements to show how that plays out. Okay, so here's a statement about series. We know that the claim is, anyway, 2 plus 2 squared plus 2 cubed plus 2 to the 4th plus 2 to various powers n always add up to 2 to the n plus 1 minus 2. And the claim is this is true for all natural numbers. The first step is to show true for n is equal to 1, show true for n is equal to 1. And for series statements, this is akin to saying show that a sub 1 is the same as s sub 1, the first partial sum. And this is usually a trivial thing. For this case, we have to show 2 to the first, which is coming from here, is supposed to be the same as 2 to the 1 plus 1 minus 2. And if this is true, then we've completed the first step. So let's say 2 to the first is 2. This is 2 squared minus 2, which is 4 minus 2, which is 2. Okay, so 2 does equal 2. That's a true statement. And you might want to try following this template for some of these other statements about series. But there are other types of statements that can be proved inductively besides series. So let's look at a statement about divisibility. And so I wanted to try a couple of these statements about divisibility. Let's prove, or we're going to start the proof anyway, prove that 3 to the n minus 1 is divisible by 2. And this claim is for all natural numbers. Okay, so now to show true for n is equal to 1, the first step. Hi, good morning. This is my video lecture for my little darlings. Mr. Price just walked into the room. Let me turn this off just for a sec. Pause. Back to the recording. Okay, back to the recording. Mr. Price and I had a short discussion. He says, we may not be in school for the rest of the week. You get more video lessons. Think about it. Okay, at any rate, we want to show this statement is true for n is equal to 1. But it's not just saying that. We want to actually show that 3 to the first minus 1 is divisible by 2. But you have to work that out. You can't just write that statement down. Okay, so this is 3 minus 1, or 2, is divisible by 2. And that's certainly true. Okay, divisible by 2. So the idea on this show true for n is equal to 1, you have to show the very specific statement that you're trying to prove is true. And you can't just write down show true for n is equal to 1. You have to take the particular statement, whatever it is, and replace n with 1. Okay, let's go back to our list of statements to prove. There's a number of divisibility proofs. You can try those. Again, just step 1. Okay, inequalities. Statements involving inequality. So here's another type. Let's see what we've got here. We've got, let's go down to the second one here. We want to show that 2 to the n is greater than or equal to n plus 4. And now this statement has restrictions. It says for all natural numbers, but then it says n has got to be greater than or equal to 3. So our base case, the first domino if you want, the base case is not show true for n is equal to 1. In fact, it's not true for n is equal to 1. You put 1 there and 1 there, you would get 2 is bigger than or equal to 5, and that's not true. Okay, so for this case, for this particular statement, the base case would be to show true for n is equal to 3, because that's the smallest number that it's supposed to be true. Okay, so let's see if that actually falls out for this problem. We're going to take 2, replace n with 3. We have to show that's greater than or equal to 3 plus 4. Okay, so sure enough, this is 8, and it is greater than or equal to 7. So true for n is equal to 3. Another inequality statement. We'll just try one more here, and then I'll let you try A and D. So try this one and this one on your own. But let's look at D. D says 3 to the n is less than or equal to n factorial, and this would be for all n's, for all natural numbers, with the restriction that n has got to be greater than or equal to 7. So this one doesn't even start until 7. Okay, so what we have to do is we have to show true. This is the base case again, the first domino to fall. Show true for n is equal to 7. And for some fairly large numbers here, so I have my handy dandy calculator we can look at. Let's look at 3 to the 7th. Okay, 3 raised to the 7th. That's 2187. 3 to the 7th less than or equal to 7 factorial. 2187 is supposed to be less than or equal to 7 factorial. Let's see, factorial button, 7. It's under the math, arrow over to probability. There it is, option 4. 7 factorial is 5040. So sure enough, this is true, 5040. Okay, so you can put a check mark there, and that is true. And, you know, by the by, you might want to just note that if you actually tried n is equal to 6, I don't think this will work. So is 3 to the 6th less than or equal to 6 factorial? Well, the calculator again comes in handy. Let's see, 3 to the 6th is 729. 729, and is that less than or equal to 6 factorial? Let's see, 6, math, probability, factorial, and that's 720. And in fact, that's not true. Okay, so no. This particular statement that is to be proved only is valid for numbers 7 and up. So that's the restriction there. Base case starts at 7. Okay, so let's go back to the top of this. Once you show that the very particular statement that you're trying to show is true for n is equal to 1, the next thing is to do this inductive step. Okay, so the idea is we want to assume the particular statement is true for n is equal to k, and then somehow show that that statement is also true for the successor, n is equal to k plus 1. And again, I want to do just a couple of these series statements. Let's try C here, and you can try all of these. So in C, we were trying to show, let's see, 1 squared plus 2 squared plus 3 squared plus 4 squared plus dot 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 plus n squared. This looks like a sum of squares, right? Sum of squares is supposed to be equal to 1/6 times n plus 1 times 2n plus 1. And this particular statement is supposed to be true for all natural numbers. Okay, now assuming we've cleared the hurdle of showing true for n is equal to 1, let's go to the assumption stage. What are we supposed to assume? Okay, so we are supposed to assume for this proof that this is true for n is equal to k. But you can't just write that. You have to write this statement true for n is equal to k. So this is what I would like you to write. Assume that 1 squared plus 2 squared plus 3 squared all the way out to k squared, right, replacing n with k, is supposed to be equal to 1/6 times k plus 1 times 2k plus 1. Okay, and that's going to be our assumption step. But after that, you really should write down what you need to show. Okay, so same proof. We need to show true for the successor, which would be n is k plus 1. And again, you can't just write that. You have to write down exactly what you want to show. We want to show that 1 squared plus 2 squared plus 3 squared plus dot, 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 plus now the successor is going to be k plus 1 squared. Make sure you wrap that in parentheses. 1/6 stays 1/6. This k becomes k plus 1. This k plus 1 becomes k plus 1 plus 1. And yes, I know you could write that as k plus 2. And let me just go ahead and write down k plus 1 plus 1. And this one would be 2 times k plus 1 plus 1, like that. And that's what we need to show. Okay, so this is like the second part of all induction proofs. You're setting it up. You make the assumption true for n is equal to k, and then need to show true for the successor, k plus 1. Okay, and that works for every induction proof, whether it's about series or whether about divisibility. Let's try the second step for a divisibility proof. Let's suppose we were going to show this first one, 3 to the n minus 1 is divisible by 2. And the claim here, this is for all natural numbers. Now we've already done the base case. We showed that it was divisible when n is equal to 1. But now here's our assume case. We're going to assume true for n is equal to k. Now what does that mean in this case? It means 3 to the k minus 1 is divisible by 2. Frankly, there's probably a better way of writing this. I'm going to write it this way. 3 to the k minus 1 is going to be 2 times some quantity, and I'll just use a for a quantity. Divisible by 2 means that 2, or think of it this way, divisible by 2 means that this expression has a factor of 2. So 3 to the k minus 1 is equal to 2 times something. What do we need to show? Need to show true for n is equal to k plus 1. But again, specifically, what does that mean? 3 to the k plus 1 minus 1 is divisible by 2. That's what we need to show. Or better yet, you can say 3 to the k plus 1 minus 1 is equal to 2 times some quantity. And it's probably not going to be a. It can't be a, in fact. But let's say some other quantity b. So you have got to show that this, in fact, has a factor of 2. Okay, so that would be for all divisibility proofs. And you can sort of try any one of these. We'll post all these answers over the next day or 2 or 3, depending when we come back to school. Let's look at a statement involving inequalities. Okay, so again, we're doing this part 2 of the induction template. Let's go to B. I think we started that one. We had 2 to the n is supposed to be greater than or equal to n plus 4. Remember, this was valid for all natural numbers with the restriction that n had to be greater than or equal to 3. We did the base case. We showed that it was true for n is equal to 3. Let's look at the assumption. We're going to assume true for n is equal to k. And in this proof, what that means is 2 to the k is going to be assumed to be greater than or equal to k plus 4. What do we need to show? We need to show true for n is equal to k plus 1. For this proof, that means we need to show that 2 to the k plus 1 is bigger than or equal to k plus 1 plus 4. Okay, so again, setting up the assumption and then the successor property or the inductive property if this is true, assume this is a fact, how can you get to here? Get to this. Now, how you get to there, that's the crux of all inductions. Let's go back to our template. Again, hopefully you have this printed off, or at least you're looking at it. How do you get from the assumption to what you need to show? Well, for every statement about series, and this is frankly what we're concentrating on, for series, you simply add the successor. That will always work. Add the successor to each side of the assumption. The series proofs tend to be straightforward. They do tend to be a lot of writing. You've seen a number of series proofs that we've done, and I'll just go ahead and do one of these. I sort of like this one about the sum of squares. You actually will use that in calculus down the road. So let's see. Well, in fact, I think we already have this up here somewhere. Where's our sum of squares? There's our sum of squares. Okay, so we showed it true for n is equal to 1, or maybe we didn't. I think we should probably go back and just pick up the base case here. Let's show this is true. Show true for n is equal to 1. Remember, that means the first term has got to be the first partial sum. And for this particular statement, we're doing this one right down here. Okay, so for this statement, that would be, we have to show that 1 times 1 plus 1, that's coming out of here. Oops, didn't want to do that. That's coming out of here, right? And that's supposed to be equal to 1, whoops, wrong one. We're doing sums of squares. Sorry about that. Okay, sums of squares. So, sums of squares. A sub 1 was simply 1 squared. Yeah, sums of squares. And the right side, we're supposed to have 1/6 times 1 times n plus 1 times 2. Whoops, we're putting 1 in for n. 1 plus 1 plus 2 times 1 plus 1. Okay, so we have to show these are the same. Obviously, the left is right, the left is 1, and the right side, we have 1 times 2 times, what's this, 3, right? So this is 1 is equal to 1/6 of 6, right? And so that's true. 1 is equal to 1. Okay, so this is true in the base case. But let's go back to our assumption. Here's our assumption. This is what we need to show. Now, for every series proof, these always work the same way. Let me see if I can drag this down a bit here. Okay, well, I'll just keep extending the page. What we want to do to this assumption, we will always add the successor to both sides. So the question is, what comes after k squared? And that would be k plus 1 squared. So you're going to add it there, right? And you're also going to add it here. Whether you add it to the front or the back, it doesn't much matter. K plus 1 squared. Okay, so, how does this play out in a proof itself? Well, let me pull up a new page. Here's our assumption. 1 squared plus 2 squared plus 3 squared plus k squared, I'm going to leave a gap here, is equal to 1/6 times k now, times k plus 1, times 2k plus 1. That's our assumption. Our goal down here, the goal was 1 squared plus 2 squared plus 3 squared plus k plus 1 squared, right, is supposed to be equal to 1/6 times k plus 1 times k plus 1 plus 1. I'm going to write that as k plus 2. And then times 2 times k plus 1 plus 1. Okay, so somehow we've got to get from this assumption down to the goal. And again, just go back here. Here's our assumption, right? This is the assumption in the red. Okay, and then we're going to somehow get from there to here. And for series proofs, that always works by adding the successor. So if we go back and we say, okay, let's go ahead and add the successor to both sides. We have, let me grab a different color here. Okay, 1 squared plus 2 squared plus 3 squared plus dot, 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 plus k squared. We're going to add the next term, which is k plus 1 squared. And on the right side, we're going to add k plus 1 squared. We're adding the same thing. The addition property of equality says you can always add the same thing to both sides of any equation, and it's still legitimate. K plus 1, whoops, k times k plus 1 times 2k plus 1. Okay, so that's a true statement. If the assumption is true, this has to be true by the addition property of equality. Now, to get from there to the goal, well, notice the left side is already there. The left side matches exactly, that is exactly this. So I suppose we could just write ditto, ditto. Now, some people say, well, wait a minute, it doesn't quite look exactly the same. There's your 1 squared, and there's your 2 squared, and there's your 3 squared. But where did the k squared go? Well, the k squared is sort of assumed into this ellipsis, right? So this is a series, the last term being k plus 1 squared, and there it is. Okay, so the left sides are perfectly good. We just have to show that the right sides match up with the right sides. Okay, so let's see what we've got here. You can work a couple of ways here. If you work backwards, that's useful for a lot of folks. We have 1/6. This is k plus 1, k plus 2, and this, if we multiply out, what's that? That's 2k plus 3. That's the right side, and somehow on the above up here, it has to make, this is 1/6, sorry. It has to be exactly the same thing. I suppose what we can see is we have this factor of 1/6. We might want to write this one as 6/6 times k plus 1 squared. That way we have that 1/6 sitting there. Okay, so that sort of makes sense. Let me see if I can drag this down a little bit to give me a bit more room. I find that when you're doing these proofs, you do a lot of scratch work off to the side, a rough draft. And then when you're trying to get to your final proof, plan on using like a whole sheet of paper, because there's usually a lot of room that you're going to need here. Let's see, what have we got? Let me bring the 1/6 out, so that matches up with that. Now we have k plus 1 squared, and here we have a k. I factored out this 1/6, that's the brackets. So we have k times k plus 1 times 2k plus 1. This is interesting. If we look at these two terms, here and here, I see something they have in common as well. They have a k plus 1. So let me go ahead and factor that out. So now I have the 1/6, and I have a k plus 1. Okay, now what's left? I still have a k plus 1 from here. And here I have a k times 2k plus 1. Okay. Let's see, so just sort of matching up what we have. We've got the 1/6, that matches. We've got the k plus 1, that matches. Somehow this is supposed to be that. And I bet you if we just went off to the side and did a little bit of scratch work, we would find that those would in fact be exactly the same. Let me move this down again just a tad more. Okay, so let's see. We have the 1/6, we have k plus 1, and this is k plus 1 plus 2k squared plus k, if I distribute there. And so I have 1/6 k plus 1 and 2k squared plus 2k plus 1. All right. Those don't match. Well, such is life. We're going to have to do some scratch work here and show that these actually are the same. I do know they work. This does work. I see where I went wrong. There was a 6 right here. I forgot to put the 6 in. So there should be a 6 there, which means there's a 6 here, which means this is 6k plus 6 when I distribute that. And on the right side now, we've got 2k squared plus 6k plus 1k is 7k plus 7k, and the constant is 6, not 1. Okay, and I bet you if you just double check, that will work. There's your 2k squared, there's 3k, and 4k is 7k, and there's your 6. Okay, so it does work. Now again, when you're doing series proofs, and will you have to do one this complicated on the test? No, we're going to stick with the arithmetic series. So just think constant differences. This is a non-arithmetic series. But the idea of adding the successor to both sides is the key to working all induction proofs about series. So here's our template again. And if we look at this, show true for n is 1, that's the base case. Assume the statement is true for n is equal to k, then show it's true for n is equal to k plus 1. You're always going to do that by adding the successor to every side, to both sides, for every statement about series. And again, if you can do that for arithmetic series, you'll be in good stead. But I do want to show you, how might you prove other statements? So let's do a divisibility one, for example. Okay, so back to divisibility. We had, let's see, here's a divisibility one. Okay, show that this is divisible by 2. And it does work in the base case, n is equal to 1. Remember, the assumption would be to assume true for n is equal to k. We would be assuming 3 to the k minus 1 is divisible by 2, or you can think of it as 2 times something. And what we would need to show, true for n is equal to k plus 1. We would have to show that 3 to the k plus 1 take away 1 is the same as 2 times some other number b. Now, how do you go about doing that? Well, for these divisibility proofs, there's usually a little trick here. We start with this, our goal, and somehow we have got to show that this 3 to the k plus 1 minus 1 is evenly divisible by 2. So here's 3 to the k plus 1 minus 1. That's the same as 3 times 3 to the k minus 1. Remember, the rule for exponents is if you have the same base, you can just add the exponents. So 1 plus k, that's that. Okay, so we have that. Now let's see, this is 3. Let's do it this way. This is going to be 2 times 3 to the k plus 1 times 3 to the k, and then I still have the minus 1. So what I've done is I've broken this up into these two terms. And it sort of makes sense. If you've got 2 of them and you add 1 more, that's 3 of them. So we do have 3 times 3 to the k. Okay, and then I'm going to look at it this way. This is the same as 2 times 3 to the k. Now, what is this little back here? This is 3 to the k minus 1. And what do we know about 3 to the k minus 1? Do we know anything about that? Do we have a fact about that? Did we assume anything about 3 to the k minus 1? We assumed that 3 to the k minus 1 was, in fact, 2 times something. So I'll come down here and rewrite this as 2 times something. So I have 2 times 3 to the k plus 2 times something. Right? That was our assumption. And now look at these two. In fact, there is a common factor. So I can now write this as 2 times 3 to the k plus a. Right? Factor out the common factor of 2. And so now I've done it. This is 2 times some quantity b. And that's what I needed to show. I needed to show that 3 to the k plus 1 is in fact 2 times some quantity. And in the proof, I use the fact that 3 to the k minus 1 is 2a. This was my assumption. Okay. Now, divisibility proofs can be challenging, and you know, for the test, this would certainly not be one that's required. Maybe a bonus. You know, could you do something with divisibility? Let me check my time running here. Hang on. Okay, so we've been going for 30 minutes. I want to wrap this up in a class time. So I know this has been a long video. I'm going to wrap it up in another 10 minutes. But let me do one more divisibility proof. Okay, so let's see. Statement about divisibility. Let's suppose we wanted to show that this is always divisible by 5, or 8 to the n minus 3 to the n is 5 times some quantity a. How can we show that? Okay, so 8 to the n minus 3 to the n is 5 times something. Let's show it's true for n is equal to 1. N is equal to 1, 8 to the first minus 3 to the first, which is 8 minus 3, which is 5. And that's certainly 5 times 1. Okay, so it does work when n is equal to 1. Here's the assumption. Assume that 8 to the k minus 5 to the k is 5 times something, right? And now we're going to need to show somehow that 8 to the k plus 1 minus 5 to the k plus 1 is 5 times some other quantity b. And again, it's very similar to what we did in the other proof. I'm going to write 8 to the k plus 1 as 8 times 8 to the k, and this one I'll write as 5 times 5 to the k. Again, just using properties of exponents. Remember, these are ones, same base, you can add them up. And then I'm going to break up 8 times 8 to the k as 3 times 8 to the k plus 5 times 8 to the k minus 5 times 5 to the k. And I think you can sort of see where I'm headed here, I hope anyway. We know that, let's see, okay, so let's look at these two guys. They have a common factor of 5, so this is 5 times 8 to the k minus 5 to the k. We can see that. Let's see, I'm trying to show this is divisible by 5. Okay, I got a factor of 5 there. Plus is 3 times 8 to the k. You know, I probably broke this up the wrong way. I like this. Okay, mathematics at work. I'm going to have to play with this one and come back to it. I don't want to drag this lecture on. Somehow this has got to be equal to 5 times some quantity. And this is obviously 5. We know 8 to the k minus 5 to the k is 5a. So 5a, we've got that. But how are we going to get this guy out of there? I'm not sure yet. Okay, so I'll play with this one and get back and look at this guy. Okay, let me check my time. So I've got 6 more minutes. Let me start a inequality proof. And we've done the base case in all of these. We've written down the base case for B, right, for B. And I think we've also wrote down the assumption and what we need to show. But I'm going to play with that one just for a little bit and see if we can get any headway on that. 2 to the n greater than or equal to n plus 4. This is valid for all numbers greater than or equal to 3. The base case show true for n is equal to 3. We did. For n is equal to 3. That worked. Okay, so here's our assumption. 2 to the k bigger than or equal to k plus 4. From there, we need to get to this. 2 to the k plus 1 is bigger than or equal to k plus 1 plus 5. So somehow we have to get from there to there. No divisibility here. There's no series. We're not adding anything. I'm just going to play with this particular assumption. Let me multiply both sides by 2. Okay, so I'm going to do that. I'll have 2 times 2 to the k is, and multiply this one by 2, 2k plus 8. Okay, so if the black was true, which we assume to be true, then this has to be true greater than or equal to by the multiplicative property of inequality. You can always multiply both sides of any inequality by a positive number, and the sense of the inequality stays true. You know, so how are we going to get from there to here? I guess that's the next step. Well, we do have the left side matches up exactly, 2 to the k plus 1. So that is true. And we have it larger than or equal to 2 to the k plus 8. What we really want is to have this larger than or equal to k plus 6. So I guess the question is, can you show that this is larger than that? And that's usually pretty easy to do. I'll go off to the side. Is 2 to the k plus 8 larger than or equal to k plus 6? Question mark. Well, let's subtract k from both sides. And then we'll subtract 6 from both sides. K greater than or equal to, or subtract 8 from both sides. So is k larger than or equal to -2? Yes. Since we know that k has got to be bigger than or equal to 3, it's certainly bigger than or equal to -2. This is a true statement. This is a true statement. This is a true statement. This is a true statement, yes. So by transitivity, we have 2 to the k plus 1 is larger than 2 to the k plus 8. And we've shown that 2 to the k plus 8 is larger than k plus 6. So if A is bigger than B and B is bigger than C, we can make the statement that 2 to the k plus 1 has to be bigger than k plus 6. We sort of hop over this middle stage. Okay, and that's by transitivity. Okay, in all instances, whatever the proof is, and remember the ones that you're really going to be focused on series proofs, in particular arithmetic series. So that's the ones we're really stressing. But in all series proofs, make sure you end with a concluding statement. So I do need to have this concluding statement at the end. So at the end of this one that we just did here, I could write, therefore, by the mathematical induction property, we have shown that 2 to the n is larger than or equal to n plus 4 for all natural numbers, with the restriction that n was bigger than or equal to 3. Okay, QED. Remember, you could write QED or you could write a little square, solid or filled in. I don't much care. Okay, so that's the end of this lecture. Now again, Mr. Price seemed to think that I'm talking now on Wednesday, Ash Wednesday at 11 o'clock in the morning. Mr. Price seemed to think that we may not be in school tomorrow, which is Thursday, and he said we might even be out of school on Friday. Well, if that's the case, obviously our test will be the following week. I'm going to post another lecture on this tomorrow, so please check your My Crew, check your notes, and I'll go ahead and write down some other stuff about these particular statements that you can try playing with. You know, spend a half an hour a day on these, and you should be in good shape. There's lots of videos now under this topics, and so please watch those. Feel free to email me if you have a question. And I'm going to go ahead and try to play with this one as soon as I stop this video, and maybe come up with a nice proof for that, because I sort of muddled along there and never did show this was true. Okay, have fun in the snow. Bye-bye.